Hi, this is Stan Forrester, your instructor, and I thought I would offer a little bit of feedback on how to go about solving the written problem. Some of you are having a little problems with that. So let's go ahead and let's get started. This is not the same situation you have. I have an equilateral triangle. We'll call it 1 meter on a side. We'll just call that 1 meter. Here, each of the sides is 1 meter. And the charge, each of the charges, irrespective of sign, is 1 coulomb. That should make the math a little bit easier. Okay. So Coulomb's law says that the force exerted between any two of them is just going to be K sub E times, well, it's Q1, Q2, but they're both the same. So it'd just be 1 coulomb squared divided by the distance squared. Okay. So 1 coulomb times 1 coulomb is 1 coulomb squared divided by 1 meter squared. So really, the force involved is going to be 8.99 times 10 to the ninth newtons. Okay. Now, the case of the electrostatic constant has units of newtons, meters squared per coulomb. Okay. The coulombs units with the two charges here are going to cancel with the units in the electrostatic constant. And the whole Newton meters squared is going to be canceled by dividing by meters squared. All right, so we have the magnitude of any one of the charges, acting on this top charge right here. And I'm going to go ahead and I'm going to use green for that. All right, and so this is, let me see if I can make a better arrow here. So the force between the two negative charges is going to be repulsive, just like that. And it's going to be attractive between the two opposite signed charges. Okay, let's take a look at that. All right. And so you look at this, and they're going to be about the same magnitude because they have the same magnitude charge quantity. So the forces are going to be about the same. We can see that this is going to add up. There's going to be a total force here. Let's use purple here for the total force. It's going to be something like this here. Okay. And so how do we add those forces up? Okay. So let's make this way thinner. There's a coordinate system right here. Coordinate system right there. It's your X and Y coordinate system. And we're going to go ahead and we're going to take our angles here. Here's the first angle. Okay, this is 90 plus 90 plus 30. We can get that from the properties of an equilateral triangle. So 90 plus 30 is 120. It's 120 degrees right there. Okay, and this one here, this is going to be 180 plus another 60. So 240 degrees. All right. And then we're going to go ahead and we're going to use our trig formulas to figure out what the um, what the argu what the magnitude of the these components are. Okay, so let's do the x component first. Okay, so that's going to be whatever this magnitude here is. So this is, I'm just going to call it 9 newtons times cosine of 120 degrees. Remember, we're adding up um, the magnitudes of the components in order to get the magnitude of the net component. So cosine of 240, I'm off the, am I off the scale here? What am I doing here? Right there. Look at that, 240 degrees. Okay, and I think you're going to find that 120 degrees and 240 degrees cosine is going to give the same answer. It's going to give the same negative answer. But they're going to add up. And so we have component in the x direction like this. Now, if we look at our y component, okay, it'll be 9 newtons. Okay, and okay, to get the y components, we have to use the sine. So we have sine of 120 degrees plus the sine of 240 degrees. And you're going to find that these actually have opposite signs. There's going to be a magnitude, but they're going to have opposite signs, and they're going to add up to 0. The sum is equal to 0. Okay, so your y component is 0, right? Now you're going to do something very similar with your arrangement. You'll figure out what the various components are, the x components and the y components, and then you'll have to combine those x and y components in order to find the total magnitude. Remember, your total magnitude of your total force, here you go, we use absolute value bars for the magnitude, is going to be the square root of the components added in quadrature. Okay, so we're going to take whatever that f component was, we're going to square it, and we're going to add it to whatever the y component was, and square it. And then that sum, we're going to take the square root, and that's the magnitude of the total force. Okay, so that's already 7 minutes. If that's not enough assistance, you need a little more, more of a hint, let me know, and I'll try to provide that for you.